Rényi divergence relative entropy.
I think I will sit to spare time. Okay. So if I understand well, we have like a small data problem. So I have to conceive a lot of information in a very small amount of words because we are super bounded in time. So, okay, so this is a talk about kind of an unexpected and possibly intriguing result about which I don't know if it's interesting or not, and that's why I'm proposing it to you. It's a kind of an outcome of a more solid construction on which I've been working with Professor Pistone and Luigi Malagò in the last year. And so basically the context is the attempt to construct a Lagrangian Hamiltonian mechanics on a statistical manifold, okay, in a non-parametric fashion. That's basically motivated, sorry. That's basically motivated by the fact that there is a growing interest in studying dynamics of probabilities on statistical manifolds in general. And I have a list of references, which is just related to what I've been reading. So it's out of completely, not a complete list, of course, but my interest personally is also related to the fact that I would like to import in physics, I'm a theoretical physicist, a lot of new ideas coming from probabilistic and information theoretic, if you want, the probabilistic viewpoint. So in statistics, algebraic statistics. So the two main qualifications of the work I'm going to propose are that we are focusing on the positive probability function on the finite sample space. Professor Pistone will talk about infinite dimensional sample spaces probably in the next talk. And that discussion would be, this formulation would be in completely non-parametric. So along with what Jesse was saying somehow. And then that, the core basically of this formulation is that we're going to describe the statistical manifolds in terms of statistical bundles. So when probabilities comes together with random function would characterize them, which may be the score or some other statistical feature which we want to enhance in our description. So okay, so let me start from the very basics. I'll try to be short. Okay. So we start from a sample space. We construct, the first geometric representation of our manifold of probabilities is an n-1 simplex, where n is the dimension of the sample space. And in standard information geometry, statistical model is a parameterized set of probability functions, right? So the point of view of information geometry is that the statistical model must be viewed as a submanifold of a manifold of probability function. That's a standard, if you want, along with Amari. So now focus on the topological interior of this simplex, as we do always. So the set of strictly positive probability functions. And what is the idea about using a metric? It's that what Rao proposed in 45. So import a Riemannian geometry, okay, via some one-to-one mapping into your set of probabilities in your space, which is a set of probabilities. And then basically, my one-to-one mapping on the positive orthant of a sphere, and then you can define, a metric by just pushing forward what you have as an inner product on the sphere, which is a Riemannian manifold where everything is under control on a set of points. Okay, so this is the origin basically of the Fisher-Rao metric and all the machinery. So now what we want to do is, and what Pistone proposed actually to do since this decade, is a non-metric, non-parametric presentation of information geometry. As I was saying before, realize we had this joint picture, okay? So we have a probability simplex together with a set of p-integral functions over it. With this function basically will be described in terms of vector bundles on this base manifold, which is the open set of positive definite probabilities. Okay. So, okay, can you give me like 10 minutes?
Yeah,
I feel the stress of something happening behind me. And
Sorry.
and I cannot feel.
I'm sorry.
No problem. So, okay. so let me give you some definitions. I will be also maybe too fast on these points, but so for each P, so we consider the L2 space, okay, this want the Hilbert-like structure on in terms of function, a random function over the probability space, which is endowed with an inner product given by the expectation value, the standard basically in a product that we want to define not in terms of a metric, but in terms of a pairing, if you want, on this vector bundle. And we use the standard decomposition, orthogonal decomposition, where our function can be defined decomposed in terms of expected values and basically centered valued functions. Okay, so the statistical bundle is defined as to be the set of of couples of points and random functions or vectors, such that the probability stayed in our open set, the internal simplex, and the U is part of these centered values in the space. Okay, so now since we are in delta 0 omega, so we can represent this set of probabilities as a maximal exponential family. We want to think of it as a maximal exponential family. This can something we can always do, of course, because we are definitely positive. And we need to then to characterize this model space on which we build as a statistical bundle in terms of an exponential, characterization. So we do that.
Zero mean?
Sorry.
What was the substitute?
So I was expecting very fast. So this 0 is this. So the definition is basically in the interior part. Okay.
No, on L.
L. L0. Yeah. So L0 is the part of L as is defined upstairs. So you decompose the L2 space in terms of constants plus things which are centered around on the constant. So the expected value of these quantities is 0. In this sense, is a tangent space. Okay. Okay. So we want to define now an exponential statistical bundle. Okay, it's the vector bundle tangent to the maximal exponential family, which is defined as S epsilon. And this is realized by choosing a suitable exponential atlas of charts. Okay, the atlas of charts is given by this map, which the exponential is basically the inverse of a retraction map. Okay, so we express probabilities Q in this case with respect to the reference probability P as basically as the ratio of information, so the log Q over minus the log P, so statistical information. Okay, so this allows us to express Q as an exponential U centered with respect to variables U centered around the mean, where now Kp is the cumulant function, which is related to the expectation value of U. Okay. So the exponential statistical bundle has also dual space, of course, and which is algebraically dual to that, but it has a different geometry substantially, which is induced by different affine transports. So I forgot to say before that in order to construct this structure, we need to specify a map, so an atlas of charts, and also a transport, a parallel transport. And the most natural choice of parallel transport associated to an exponential family is an affine choice of transport, which will be given by this U E PQ, which means exponential transport, which is basically, as you see, a shift from a fiber centered on a base point, which is a probability P, so to the fiber associated to center value around another probability point. So we do the same for a mixture atlas, and we get this basically affine, dually flat structure, which reproduces what we have in standard information geometry, if you want, in the metric, in the Riemannian information geometry. So we have to check that the transports are conjugate with respect to duality pairing. And basically, we can, as I was saying, we can reconstruct everything else with respect to the generating function, which is the cumulant of our exponential family, Kp, which is nothing but is related to the Kullback divergence. Now, as I was saying, this formalism, now we have to believe me because I couldn't be very clear, but is basically providing a non-parametric extension of a tangent bundle of the Riemannian manifold with Fisher metric, and it accounts, so it's for a dualistic affine structure, which is proper of a standard Amari's information geometry, if you want. But it is also functional formalism. So it's an algebraic approach, which can be extended to infinite dimensional, to the case of infinite dimensional sample space, and can be also generalized to logarithmic representations. So Q deformations, Wasserstein geometry, and so on and so forth. So it's very general. That's why it's very nice. Okay, so now we want, as I was saying at the beginning, so the framework is a mechanical framework. So we want to do mechanics on that. So we want to see how particles, which are probabilities, move on our simplices. So we want to define a velocity. So a velocity in this framework is basically defined as a score function. Okay, so the way you do it is you go the chart by your modeling vector space. You calculate the derivative in time. So maybe it's easier if I just to here. Okay. Your derivative in time, which is here. Okay, so you take a curve. Okay, take a curve in your statistical bundle. Has two components. One is the probability, which you can see as a one-parameter model. Okay, on your simplex. The other one is the vector associated to on the statistical bundle. So if you want the tangent vector, and take the derivative. So this is a curve lift on the statistical bundle. You take you map it in chart. You take the derivative in time, and you see that you get something which is the derivative of the log of the curve for the first component, transposed on the reference probability. So now, basically, what is convenient to do is to go to the moving frame, as Rita was suggesting before, and then look at everything in terms of statistical, purely statistical quantities, which are not dependent on coordinates, on parametrization. In this case, so we get the score function. So our velocities are scores, which is kind of different from what you get when you have a tangent space, which is in the Riemannian sphere. In that case, we would have Q dot. Here we have Q star. Okay. So for the second component, then we realize that our geometric construction works because we don't have we are derivating a vector, okay, on a fiber bundle, and then we get a covariant derivative, not just a simple derivative. A covariant derivative defined with respect to the specific transport we defined before. The same thing we can do. We can do it for the dual representation, and essentially what is important here is that the couple of covariant derivatives are compatible with the duality pairing again. So everything is consistent with the dual structure that you have. Now, the nice thing is that this bundle construction can be extended now. So far we were looking at velocities. So if you want, we were looking at first order dynamics, which is gradient, basically gradient descent, and this is standard somehow. But what about accelerations? I mean, it's not a statistically clear notion what we mean about acceleration, whether the accelerating flow can stay within the simplex or not, and so on. How do you define it? These standards, this setting of the statistical bundle allows you to define it in a natural way by simply going to the second statistical bundle, right? So you go to the second statistical bundle, you consistently, with what I showed before, define your derivatives in times and covariant derivatives in times, and you get an acceleration, okay? You can do it in many ways because you have a dual description on the, if you want, cotangent bundle or dual statistical bundle. You can calculate the dual acceleration, and nicely the two combine to give you the Riemannian acceleration, which is another double check that our structure, our dual Hessian structure is preserved in parallel to what you have in standard information geometry. So I need to be very quick. So the statistical bundle now, so it's suitable for Lagrangian and Hamiltonian mechanics because we have, first of all, we have a vector bundle, we have tangent space, cotangent space. We know what is the map between these, and we have a proper, acceleration description. So we define an action integral. How do we define an action integral? We take a Lagrangian as a scalar function, basically, from the statistical bundle to R. We define an action as it would be defined in physics, confined now points are probabilities, and we actually derive Euler-Lagrange equation consistently. So I don't want to show, I will not show you how, but everything works. What I didn't show is that we have to generalize also in a notion of gradient. So it's not just here, as in standard case, you have a derivative of the fiber derivative of the Lagrangian is equal to the gradient, the spatial gradient of the Lagrangian. So this is the natural gradient, and this is a gradient on the first statistical bundle, which is nothing but a fiber derivative in a non-parametric fashion. Okay. So we can do a Lagrangian transform consistently as long as we have a one-to-one mapping between the two bundles. This is important because it's not possible to do so far in infinite dimensional case. So what the basically what I want to show here is that we can define an Hamiltonian in any case, and we can have an Hamiltonian consistent Hamiltonian mechanics, and we can do optimization if you want on this. So this is an example. We can, the most trivial example is a quadratic form. We can define our Lagrange equation for a quadratic Lagrangian, which would be the free particle, okay? And since we are in a computational section, I wanted to show you that you can also plot these things and it works, okay? So, but now the topic, which is the topic I want to focus on, is that I mean, being in a fully statistical setting, we want to do something different from what we do in physics, right? We want to substitute what is a standard quadratic form, which is given by a kinetic energy, v squared, 1/3 v squared, with a divergence. Can we do that? Is it properly, is it well defined? So the answer is yes. So divergence, okay, maybe I don't need to introduce this since I have lack of time. So to define structure of the statistical bundle, every divergence is associated to a free Lagrangian function. I mean a kinetic term, if you want, a norm, by the canonical exponential mapping we were defining at the beginning. So basically, you have a mapping, a natural mapping between 2 points, and the point and the velocity, right? This is due to the fine structure that you set that is naturally set by the exponential manifold. So given these, okay, then this is always possible. There is a correspondence between every divergence into what I call divergence Lagrangian, and conversely, okay? So the canonical example is the Kullback Leibler Divergence, which in a very specific, the most simple case where the 2 points are related by an exponential arc is nothing but the cumulant. So it's a nice function to study, okay? So what if I use this divergence, this KL, in a specific case, the cumulant as a Lagrangian? I call this a dissimilarity action because it's basically an action built out of a dissimilarity measure, okay? And I want to use this.
Please, yeah, please, 1 minute. 1 minute,
okay. And I want to use this to define a length, basically, a geodesic problem, okay? So this is not homogeneous action, basically. So it's not a good information length, right? So we tried, but we failed in a sense, but still we can homogenize it. Okay, so what if we homogenize it as we do in standard covariant physics, okay? Let's try to homogenize a KL divergence. So introduce a formal time parameter such that basically what was your time and it becomes a function. This is nothing but the reparametrization of the curves, okay? The integration variable t becomes an independent dynamical variable, in fact. So instead of having a statistical space now, or statistical bundle, we have a statistical bundle plus time, okay. So now, if we reparameterize the action, the function, the action, so if you reparameterize the time along the curve on which the action is evaluated, we find this expression, and basically we can reabsorb some terms in order to define what we call an homogeneous Lagrangian, okay? So this homogeneous Lagrangian basically is nothing but a scaled divergence, okay? Fair enough, there is not much about that, but there is an interesting result, two interesting results. The first is that the homogeneous Lagrangian is associated to a family of scaled Kullback Leibler divergence, corresponds to the definition of a half Rényi divergence, okay? And I will show you in 1 second why. The second is that the homogeneous divergence also provide this statistical bundle with a sort of generalization, even if it is not a generalization of the Riemannian description, which is a Finsler geometry. So, okay. So this is the point. So basically we have this scaled object. This is an homogeneous divergence, an homogeneous KL divergence. you open it, you express it in terms of the unscaled originary variables. And as a magic, you get something which you recognize as being basically an alpha Rényi relative entropy. Okay. So in particular, since every f dot is from the point of view of your diffeomorphism or a parameterization value is allowed, being a Rényi divergence fix what is f dot. So it basically is forcing you to restrict to f which are linear in time. Okay. Okay, the question is whether there is a covariant, a consistent covariant description in statistics where also time can be expressed as part of a sample space. The second point is just that, as I was saying, this is a more technical result. So this divergence gives basically is nothing but this scaled divergence becomes gives you a Finsler metric on your space, and we have to prove it. So we just do it, and you prove it in calculations which are not interesting. But the point is that, as I was saying, so the divergence fulfills all the standard all the requirements for being a Minkowski norm. Okay, and this is also nice because once you have this Minkowski norm in your extended statistical bundle, this also provides you with a contact form on the level set of the norm, and then it opens another windows on this. Why this is interesting? Because this is related to non-equilibrium, to open systems, basically. So I'm really out of time. So thank you very much.